hopefully I can get through this without my voice cutting out. I get really excited when I talk about tillering, and I've done this 3 times now, so we'll see. But yeah, last thing between you and lunch, so hopefully we can make it a good use of your time. My name is Rachel, and I'm a PhD student, graduate research assistant at K-State. Go Cats! My advisor is Dr. Ignacio Ciampidi. If that name is familiar to you, he's the cropping systems extension specialist and a professor there. Does a lot of work in crop production. So I have the opportunity to work with him, do a lot of extension type stuff with him. Whether it's something to be proud of or ashamed of, or I don't really know, but it is what it is, and I've kind of accepted it. My advisor, farmers on Twitter, other people I know have nicknamed me the Tiller Queen, and I just kind of roll with it. But the reason for that is because all of my PhD work is on corn tiller development and the physiology behind that, the impacts on yields, those kinds of things, and then also management for low-density corn in Kansas. So that's kind of a little bit about me. I got my bachelor's degree at Missouri State in Springfield. I'm a South Central Missouri native, so yeah. All right, so let's talk about tillers. First thing I want to do is do kind of an introduction. So when we think about different crop species, like wheat and sorghum like I have up here, but also non-grasses like alfalfa and some clovers, tillering is a natural part of how they respond to their environment, right? It's a plasticity response that they have to make the most of the resources that they have available to them. In wheat and sorghum, we usually probably like to see tillers. We manage for that, expect that. That's something that we see favorably. When we're talking about corn, which is also a grass, okay, it has the same natural ability that those other crop species have, but we view it very differently in corn. So we don't talk about corn tillers very much, but when we do, like you were saying, there's a lot of really strong opinions about corn tillers. People have a lot of very strong feelings about corn tillers. When you're at an extension meeting with a group full of farmers and you start talking about corn tillers, you can open a can of worms really fast, right? So we call them suckers. Everyone calls them suckers. It's kind of a negative thing. We don't like them. But before we get into that too much, why do plants tiller? What is causing these plants to tiller? Because it's a natural response. It's something that happens. So what causes that to happen? And we can categorize that by 3 letters, every agronomist's 3 favorite letters, which are G, E, and M, right? Genetics, environment, and management. So with genetics, we're looking at species, which would be like the difference between corn, wheat, and sorghum, like we just talked about, right? And then also hybrid or variety. Like you guys, I'm sure, are very aware, not every corn plant will put on tillers the same, not every sorghum plant tillers the same. The hybrid has plays a big role in that. And then environment, when we're looking at the stimuli in the environment that really trigger this, because it's really an environmental response, moisture and soil fertility, so the resources that plant has, are really important. And then light and temperature. So greater light, lower temperatures actually will encourage tillering more. And management is kind of how we play with those, right? We can kind of manipulate the environment a little bit. We can pick the hybrids that we're using, the rotations that we're using, those kinds of things. But fertilization and irrigation are manipulating the resources that those plants have, right? Whereas plant density and spacing are more messing with light, planting date would mess with temperature, those kinds of things. And that's how our management could affect tiller responses, right? And one thing I forgot to mention before I got started, if you have a question or a comment, feel free to raise your hand or throw something at me and stop me and we'll talk about it. Sometimes I get really into it and I'm not really paying attention, so just holler at me if you've got a question or anything. So what do we know about corn tillers? Let's talk about that a little bit. So there's kind of 3 different ways that corn is different that I want to talk about with you this morning. First is the genetic side, so the breeder selection, kind of the history, the ancestry of that corn, the genetics that those corn plants have, right, which we've changed the way it looks, but a lot of the natural grass-like properties of that corn plant have been conserved. plant physiology, which would be when those tillers come on, how they develop, those kinds of things. And then corn management, the intensity of corn management, which has changed, which also impacts the number of tillers we see, if we see them, those kinds of things. So, corn, teosinte. I don't know if you guys have ever seen a teosinte plant before. I actually have a friend at K-State. He's originally from Nebraska. He lives in Manhattan, and every summer he plants a little patch of teosinte behind his house just because he thinks it's cool. I don't know. Whatever, to each his own. But teosinte, okay? It's kind of a cool-looking plant. So it's very branched. The grain is kind of scattered throughout, so it's more grass-like, more what we think of when we think of grasses, right? Very adaptable, very plastic, which would be the word that I'm going to be using a lot today. Very plastic, so it adapts. It can fill the space that it has. It can branch more or less. So it really fits wherever it's planted. It can adapt to that. Dent corn, as we know, is unbranched. We want a single ear, maybe two, depending on the environment we're working in, the management that we're working with. And then it's very uniform and predictable. So when we think of a field of corn, we want every plant to have a single stalk, one ear, all the same height, all look the same because it's easier to manage, right? Very predictable, very uniform, which is very different from the genetics that we started with. But some of those tendencies of the teosinte have been conserved, and dent corn can still express some of these things if it's put in certain scenarios. So, corn tillers, when are they going to come on? Are they going to come on? Those kinds of things. Let's talk about that for a minute. So the first point, if they're going to come, when are they going to come? And timing for that is V4 to V7 in corn. It is when we would expect to see tillers coming on if they're going to. So that's kind of the tiller appearance window. Favorable scenarios, which would be cool temperatures early in the season, resource abundance, which would be water, nitrogen, those kinds of things, and then hybrid selection. So like we talked about, not every hybrid is going to tiller the same. So if you have one hybrid versus another, you might see more or less tillers. So let's say we have tillers on. Now what? What can we expect? How are they going to develop? They can either be vegetative or they can move to reproductive stages. If they remain vegetative, those tillers will either be aborted because the plant will decide, you know, I don't have the resources to deal with this, I can't do this, so it's going to abort that tiller and get rid of it. Or the tiller can stay on throughout the season, and then later, during grain filling or later in the plant's life cycle, the carbohydrates, the energy reserves that are stored in that tiller can be remobilized, which means they're moved from the tiller to the main stalk to be used to fill the ear on that main stalk. Okay? Because there was a study done in 1975, which we're going to talk about in just a minute, but they studied how carbohydrates, so how energy resources were moving in a corn plant that had tillers on it. If a tiller did not have a sink of its own, which means that it didn't have an ear or anywhere for those energy reserves to go, right, it would remobilize and move those to the main stalk. But that relationship did not work the other way. So it wouldn't go from the main stalk to the tiller if there was an ear on that main stalk. Okay? So that's what I talk about. When I talk about remobilization, I'm talking about reallocating those energy resources, which is useful, right? Reproductive. So if it gets to that phase, there's two options. I'm sure most of you have seen tassel ears before, right? For research purposes, they're kind of cool, but we don't like seeing them because they're not good. Basically what happens is the tassel is partially male, partially female, and doesn't develop harvestable grain. The other option would be a typical ear or an axillary ear, which would develop off the side of that tiller, similar to what we would expect on a normal corn plant. So those are kind of the options as far as development goes. I like to throw these pictures in here anytime I can. So I'm very active on Twitter, and I get pictures from farmers across the U.S. and different parts of the world. They see tillers in their fields. They take a picture, and they want to know, like, what do you think about this? Which is kind of neat. It's kind of cool. So I just threw some of these in here because I'm going to be talking a lot about our environment in Kansas today. and I'm sure that not all of you are from environments similar to western or central Kansas. So if you're from Illinois or some other place that's more productive, or up here in Iowa, we do see tillers in situations, even in more productive regions where plant densities are higher. So like this picture from Greg in Tennessee, he has a higher plant density here. This was taken on the edge of his field. He had some tillers that were coming on in the edge rows on his corn in this field. And then Robert in Manitoba was also seeing some tillers coming on. Benji in Georgia had a lot of tillers this past year. And then this picture from Iowa is actually interesting. So Dusty, in this case, had really bad planter skips in his field, and he decided not to replant. And he was seeing a lot of tillers on all of his plants in this field with a bunch of planter skips. So that's something that you can see even if you're in an area that maybe isn't using the plant densities that I'm going to talk about later. John in Texas, we have a pretty tall corn plant, but these tillers stay pretty small. These probably developed later, so they didn't get as large. And then Nathan in South Dakota, which is probably an environment that's a little more similar to what we're going to be looking at from our Kansas studies today. So we have tillers, okay? When tillers appear, they grow directly from the node, which means that they're going to come out of the leaf sheath, okay, when they're developing. And an interesting thing, so if your corn plant is V7, which would be the last stage that we would expect tillers to come on, when a tiller appears, if it appears, if your plant has 7 collared leaves, you would expect to see the tiller coming out of the 5th leaf. So 2 leaves down from the last collared one is where the tiller will appear. And that's the case in other grasses too, which is kind of a neat relationship that you can kind of think about that. And that's the reason why V7 is one of the last stages that you would see tillers appearing, because the crown, where all of those nodes are compressed at the bottom, it's the first 5 nodes, right? So the 5th node would be the last one in the crown, which is why V7 would be the last stage that you would expect to see tillers appearing. So that's kind of fun. But when we have tillers that don't come on until V6, V7, those are more likely to stay vegetative, because by the time those tillers develop, the main plants are a lot larger, and so there's a lot more competition between the tiller and the main plant, so that tiller can't really put on as much biomass or develop as much as it could if it was earlier and the main plant wasn't competing as much for light in that situation. So when I was talking earlier about tillers being aborted and remobilized, this picture was taken at the end of the season in one of our plots that had a lot of vegetative tillers. You can see that they're all kind of dying. They're kind of green, but they're dying. So in this case, that was being remobilized, the main stock. The tillers were kept to the end of the season and then used for that purpose. Tassel ears, okay? These pictures are kind of cool. So tassel ears, it's kind of interesting. It's a hormonal response to environment. We're not really sure exactly what causes these. Damage and herbicides can also cause tassel ears to form. But in this case, that's not the case in tillers, in our plots. So when the tassel is developing in corn, both male and female flowers develop on that tassel. Hormones dictate whether the male or the female flowers are aborted, which gives us the tassel and the ear. So when the tassel is developing, if there's a hormonal imbalance when the first part of the tassel is developing, it will abort the male flowers instead of the female, which gives us kernels on the middle of the tassel, right? But then that is corrected, the imbalance is corrected, so the branches of that tassel abort the female flowers like it's supposed to, and we're left with a female middle and male branches, which gives us a tassel ear, which is kind of cool. So that's what happens. We're not really sure what causes that. We're working on that. But we don't like tassel ears because that grain is exposed, which means that insects and birds and anything else wants to eat the nice, sweet, juicy corn kernels that are developing up there, free buffet. And by the end of the season, there's either no grain left or the grain that's left is really poor quality because it's been exposed to weather and other things all season. Smut and other diseases are also an issue on these because the grain is exposed, right? So we don't like tassel ears. These are the fun pictures. So these were all taken in our plots, and these are not on the edges or like a random plant that just happened to look really good. These are in the middle of our plots. So we saw a lot of this kind of thing in our lowest densities. This plant, you can't see it very well, but there's a second ear on the back of this main stalk. So the main stalk has 2 ears, and then we have 3 tillers off this plant, and 2 of them have fairly decent sized ears. This location had good rain at the end of the season, so it was able to fill these. This was in Goodland, one of our better sites, and we have a main stalk with 2 ears and 2 tillers, each with an ear. And this picture, it's probably a little harder to see, but this is 2 plants, okay, and a 10,000 per acre density, which sounds really low, but we'll talk about that in a minute. Between the 2 plants, there were 7 ears, and all of them were like ears on 2 plants, which is wild. This obviously doesn't always happen because we just talked about the vegetative and tassel ear tillers, but they are capable of doing this. Corn plants are just amazing. They really are. Okay, management was the last thing that we were going to talk about as kind of an intro. So modern corn plants can tiller. The teosinte genetics, the grass-like characteristics of corn are still there. We just don't see them because they're suppressed with how we manage them. And the example that I'm going to use is plant density. So if you think about corn management, when we want yield responses, what we're really doing is trying to manipulate the response of each individual corn plant, right? It's on a single individual level that we're wanting that response that leads to the yield response, right, of the whole field. So if the optimal plant density is increasing, which it has been, we're putting more plants out historically, that's been the trend. What impact does that have for individual plants? Each plant has access to less light because we're putting more plants together. So at the individual plant level, we're not seeing tillering because the density is higher and they don't have access to the light that they would need to put tillers on. But if you drop the density, that changes, right? Or it can. So as far as optimal plant density goes, this figure on the bottom, we have plant density, and on the Y, we have the grain yield. And you can see that we have different shapes and colors for different eras of hybrids, different genetics. The plateau, which is where it levels off, would tell us where our optimum plant density is for getting our maximum yields, right? At that point, we're adding more plants, but we're not getting any more yields. So the trend, you can see it's moving, the plateau moves further to the right. So in the 1980s, 20,000-ish plants per acre, right, was our optimal. Now we're looking at 30,000 plus into the teens and more modern, so it's increasing over time. What do we know about tillers and modern hybrids? So I have to be really careful with how I say this because 40 years old is not old, okay? That is not old. But when we're talking about modern crop genetics, that's a pretty long time, right? Crop improvement, crop management, a lot changes in that amount of time when we're talking about genetics. As an example, the average U.S. corn yield, okay, in 1975, which was the last time that a major paper was published looking at the mechanisms of what was happening in the corn plant with tillers, which is the carbohydrate remobilization paper that I mentioned earlier, 1975. Bushels per acre, average in the U.S., 86. In 2018, we're at 176, so we more than doubled yields in that amount of time. And so, you know, our data for this is kind of dated. We don't really have a lot of modern, really digging into what's happening. And the data we do have, okay, looking at the impacts that tillers have on yields specifically, are a really mixed bag. Some people say that it increases it, some people say it decreases it, some people say that there's no impact. So different regions, different people, different years, there's not a consensus. No one really knows, right? It's kind of what you can draw from that. So everyone has an opinion, everyone has, you know, all different kinds of thoughts on this, but there's not really one answer that we can say just by looking at what's available to us right now. So what's being done? Tillering and plant density and defensive management specifically, which I'm going to talk about in just a minute, is kind of a hot topic right now. There's a lot of people that are working on this in different parts of the world. And the reason for that is the challenges that we're currently being faced with and like thinking about why we're having these discussions. So sustainability is a word that gets thrown around a lot. I'm sure you hear that a lot. But basically there's been a movement in previous years, or in current past years, that production ag is kind of expanding into less productive regions, or the regions that we do have are becoming less productive. Part of that could be due to climate change, which whether or not you believe in climate change, we are seeing more weird weather events, right? More and more anomalies in weather patterns and predictions, more uncertainty, which kind of leads into what we're going to talk about. How do corn tillers fit into this? How can we make this relevant? How can they maybe be a piece of a puzzle for thinking about this? And we're going to talk about that a little bit. So like I said, global effort in corn production systems, multiple countries around the world. The main goal of this would be to increase the efficiency of production while reducing producer risk, because that's something that's a really big concern for farmers in areas that are more affected by these climate events, or maybe with less predictable climates, because, and I'll use an example. I gave this exact presentation actually to a group of farmers at an extension meeting in western Kansas a couple weeks ago. And I had a farmer come up to me afterwards, and we were talking about this specifically. And the analogy he made is that he would rather get to third base than swing for a home run and just miss it all completely, right? So you want to at least get to third base, right? You want to at least have something. Managing defensively, making sure you at least get to third base is kind of the thought of farmers that are in these kind of situations. So marginal, what do we mean by that? Water limitations, subpar soil properties, those are kind of the main points. And so farmers in these situations would manage that in one way by reducing plant densities to match the anticipated resources they would have. So if you have a certain capacity to irrigate, you'd lower your plant population so that you could match that, and fertility also. And when you reduce your plant density, your consequence would be tiller development. Now, if you're here and you're not from a marginal environment, you're from, the ice states where you can grow really good corn, you have lots of water, and, way different than central and western Kansas, you might be thinking, why am I in this session? This is not relevant to me. She's talking about, western Kansas, and that's nothing like where I'm from. But let's make it relevant to you, okay? So more frequent climate anomalies and less predictable seasons. We're seeing weird weather events more often, okay? And that's predicted to continue. It's going to get more frequent, more intense. This is just a picture that I grabbed to maybe help us think about this a little bit. So this is the climate anomalies for temperature for June of this past year. And you'll see that, we had record warmest temperatures for some parts of the country, and different parts of the season were abnormally wet, like just weird, right? Weird weather that we're not used to. A great example that Dan Burning and I were talking about when we were putting this presentation together in 2013 is a great example. And the reason is because of what happened in 2012, okay? Terrible, terrible drought. Awful year, right? Not fun. Okay, great. Pioneer, I guess, collects the management data from producers to know the plant densities they're using, those kinds of things. And over time, plant density was going up. It had kind of maybe leveled off a little bit. But what do you think happened in 2013? It dropped, right? Because producers didn't want to have another 2012. They were more risk averse. They wanted to get to third base, right? So they dropped their plant density to try to mitigate that. So people will have, that is a response that can happen when we're looking at climate anomalies and weird weather. And so we implement defensive management strategies as a response to this. And a consequence that we can see is deficits in our plant density because we're not sure what our plant density should be, right? And that's kind of where tillering and looking at plant density and the plant's ability to adapt in situations that are maybe different from what we were expecting at the beginning of the season, that this kind of all fits together. So with that, I'm going to dig into some of the research we're doing at K-State that we've been working on, and what we're doing, the impacts, the results that we've seen. So we do have some resources available. This past year, we put an article out in Crop Science that's been published. So if you're interested in that kind of reading, we have a journal article, and then we took the journal article and made a 2-page summary out of it, and we have that published as an extension bulletin. So both of those are available. If you would like access to those, I could help you get those too. But I have the KSRE number and the DOI up here, so you will be able to access those from that. Okay, so this project. The project that I've been working on for my PhD, it's partially funded by Corteva. It's a partnership. So our plots were located in the yield test sites that the stations manage across the state of Kansas. And we did this in 3 seasons, 19 to 21. And we had 10 unique field locations across the state. So between those 3 years and those 10 sites, we didn't have every site every year, but total, we have 17 site years. So combination of location and year in this data set, which for a field research agronomy data set is fairly large, especially for one grad student to manage, right? So 17 site years, which means that we've got a pretty good set of responses and environments to look at when we're doing this analysis. So to kind of give some more perspective maybe on what I'm going to be showing you, this is the average annual precipitation map for the US. So Kansas, you can see, has a really nice precipitation gradient east to west in the state, which makes it great for different environments, like evaluating different environments with field studies. Our sites were located, you can see where in the state where they were located based on this inset, but you'll see that the precipitation gradients that we were testing cover most of the Central Plains, okay? And then a little bit east, but just to kind of maybe give some perspective on where you're located and the environments that we were doing with this. Another thing to mention, the yield levels of these sites that we were testing. Some of our more restrictive dryland environments, we were looking at under 100 bushels per acre yields on those, and then some of our better environments were 250 plus. So it just kind of, we had a pretty good range that we were looking at with these. So what exactly were we testing? We had 3 plant densities, 10, 17, and 24,000 plants per acre, which might be like, wow, that's really low. But for these environments, that's low, average, and higher end. For dryland and limited irrigation, which would be like deficit irrigation, or not deficit irrigation, just the water that they could provide during key stages, so it's still, we still have water deficits, right? So that's kind of some perspective on the plant density. Our 2 hybrids were P0657 and P0805. Both of those are prone to tillering, which we wanted in a study about tillering, probably, right? And then we had 2 tiller scenarios. So we either left the tillers intact, which means that any tillers that developed, we left them alone and they did their thing the whole season. The other half of the plots, we went through at V10, and we cut tillers off of the main stem. Now, V10, why V10? So the reason for that is because we wanted to have minimal impact on the ear development on that main stalk. We wanted to get them off definitely before V12, when a lot of that really is ramping up. We also wanted to make sure that after we went through and cut the tillers off, no more were going to come on, and those tillers that we cut weren't going to regrow. So V10 was kind of the minimizing impact on the main stalk while also being logistically possible to go through once, cut them off, because going every 3 days to these sites to make sure no more tillers was coming on was not going to be feasible for me to do, right? So that's why V10. And we did it all by hand so that we weren't damaging the main stalk. We were really careful with how we took them off. So let's get to the good stuff, okay? So yields. We had 17 site years, and so looking at all of those site years can be really overwhelming. So what we did is we took our site years and we divided them into kind of how they were responding into different groups. So we have a low or no response, a moderate response, and a high response, which is the order that these graphs are going to be in for the next couple slides. Okay. So when we're looking at these graphs, we have tillers intact and removed on the x-axis and average grain yield on the y. The letters on top of these bars, if two bars share a letter, okay, we are 95% certain that the means are not different from each other. So if they share a letter, they're the same. Okay? That's how we're going to think about that. So if we look at our lower yielding site, our less responsive site, we see that they're both A's, right? No responsive tillers. Moderate, we have an A and an AB, but they still share an A. So statistically, they're not different from each other. But if we look at our highest yielding site, this is one of our 250 bushel sites. This is one of our better sites. We see that there was a significant difference, 30 bushel advantage when tillers were intact. And this was averaged over all of our densities. So this isn't just our low density. This is averaged across all of the densities that we were testing. Excuse me. My voice is starting to cut out. So the main takeaway from this is that we did not see reductions in yields because tillers were present in any site year. So 17 site years, regardless of density, regardless of the amount of water it had, the type of soil that was there. For the two hybrids that we tested, we didn't see any yield reductions. Not to say that that could never happen, because it's impossible to test every scenario, but 17 site years with that response is a pretty decent result, right? And these publications that I showed you earlier, 2021 was not included in those, but we have analyzed data from 2021, and we didn't see reductions in those either, so it follows the same trends that we have in those other publications.
Were you surprised to see how such a dramatic difference on the high yield side?
Yeah. I was shocked by all of this. I was not expecting to see this at all. The ability of these plants to put grain on tillers and just to use the resources that they had, and it blew my mind. I was very surprised, very impressed. And I think that's one of the reasons why this project is really because everyone's kind of surprised, because I never would have guessed that having tillers on would, have a significant boost to yields, right? 3 years ago, I wouldn't have thought that at all. So it's kind of a novel thing.
How big were those, when you removed the tillers, and how much plant material were you moving?
Probably about like that. They're about that tall, maybe.
Vary in different plant densities?
On the number of tillers or the size of the tillers? But yeah. So an interesting thing with that, though, we're working now on the number of, predicting how many tillers you'd have in a field. And the interesting thing is that plant density does not seem to be significant in that. So you would have the same number of tillers per area regardless of what your plant density was in the densities that we were looking at, which means that in a 10,000 per acre, you might have 2 plants or 2 tillers per plant, but in 24,000, you might have 1 every 3 plants or so. But total per area, that's about the same. So numbers, maybe not so much, but size, so vegetative versus reproductive, how they were developing, how tall they got, that was definitely influenced by density.
Did you see more, so this is by yield environment at site location, right?
Mm-hmm.
So did you see yield impacts, greater yield impacts on lower densities?
Yes.
Right? Where you need
With tillers, yes. Because there was more of a potential for plasticity in those situations, right? The plant had more capacity to adapt when it had more space to do that, right? Yeah, good questions. So talking about the main plant and plasticity, the reason that we call tillers suckers is because we're assuming that they're robbing from the main stock, right? They're sucking yields, they're sucking resources, they're sucking water, and so we're assuming that they're reducing yields because they're sucking from the main plant. So we wanted to test that. So what we did is when we harvested our plots, we harvested tiller ears and main ears separately. We harvested everything by hand. And so, again, we have tillers intact and removed on the X. Main grain yield, so only from the main stalk, not considering the tiller grain on the Y. Again, the letters, if it shares a letter, we're 95% certain that they're the same. So in this case, we can see that each column, they share a letter, which means that they're not statistically different from each other, which tells us that tillers, just because tillers were present, we did not see main stock yield reductions in any site year. And this was, again, 2019 to 2021, 17 site years, all the densities. We never saw that. So suckers, maybe not, right? Okay. This one's kind of fun. So we have plant density on the X and tiller density, so the number of tillers on the Y. Okay? The color gradient tells us the predicted yield for that combination of plant density and tiller density. Okay? Number of plants, number of tillers. The darker colors, so the darker purples are lower yields, and the brighter yellows and greens are the higher yields. And the highest predicted yield has the star, and we're going to talk about that in just a minute. But the first thing I want to point out is the curves in these surface response plots, right? So if we look at Goodland, which was our 250 bushel, this is our highest yielding site that we had. If we look at a moderate plant density, which in our case was about 17,000, right, with no tillers, and we compare it to, or even with a bunch of tillers, and we compare it to a 10,000 per acre with a decent tiller population, so like 2 to 3 tillers per plant, we can see that the curve, the color matches. So with tillers, we were able to compensate for plant density deficits to a certain degree, right? We were able to fill that gap a little bit. But, important thing, the star is always in the bottom right-hand corner, which tells us what? We need to maximize our plant density with no tillers to get the highest predicted yield in that location. So, plant density was always key to maximizing yield. Tillers could compensate, but they couldn't give us what a higher plant density could, is basically what that means. Now, in all of these graphs, we had low response, moderate response, and high response, right? We talked about that. So what caused the high response environments to have such a high response? Like, what was it about those environments that caused the tillers to do so well? So we looked at that, and there were two main things. First is soil properties. Specifically, organic matter and clay were identified as some of the key things, which would be water holding capacity and also nutrient availability. Would probably have some role in that. And then second was a high early season photothermal quotient. Which I don't know if you've heard that word before. We're going to talk about it. But photothermal quotient, which has to do with temperature and sunlight. It's like a relationship that we're going to talk about. So what is the PTQ? Okay? So basically what it is, it's a way for us to measure the energy that's available to a plant over a given period of time. That's all it is. Okay? Energy over a given period of time. So we know that corn development is temperature driven, growing degree days, right? And the energy is sun-based. So we use the temperature and the sunlight to give us the photothermal quotient, which tells us the energy that that plant had during a period of time. So let's look at this. So if we have lower temperatures, that means that we accumulate growing degree days slower. So if we look at this graph, we can see that we have high, medium, and low temperatures, which tells us that the time to get from planting to B14, which is the example I put here, will be longer if we have lower temperatures. The number of days to get from A to B is going to take longer. So if that is longer, what that means is that all the development periods in between are going to take longer for the corn to get through those. And specifically, we're interested in the V4 to V7 window, which is when tillers will be appearing, right? So as we have lower temperatures, that window is bigger. There's more time in that. And so since there's more time that that plant can be absorbing sunlight as it's developing, we have a higher photothermal quotient in that case. On the flip side, if we have constant temperatures, but more sunny versus cloudy days, okay, more solar radiation that's available to the plant during that period of time, we have a higher photothermal quotient, okay? So why do we care about that? So photothermal quotient tells us the energy reserves that that plant could have, right? So if a plant has more energy, it's able to respond to its environment, to adapt to that, which would be tillering, whether that's the number of tillers, the energy it can put into growing those tillers. So that's one reason. Stress is something that photothermal quotient can give us an indice of, because the carbohydrate, or not an indice, it can help us overcome stress, deal with stress, because it has more energy available to put towards responding to that stress. And then filling the grain. So this would be an example of the 1975 paper that we talked about, right? Remobilizing those energy reserves. So if you have tillers that have access to a higher photothermal quotient, they're able to create more carbohydrates that can be used later in the season to fill grain if your main stock or there's other deficits in energy by that point in the season. So your to-go box, 3 things, okay? First is that corn tillers never reduced yields in any of the situations that we studied, or reduced main stock yields, neither one. And it's important to say that I'm not saying that that could never happen, right? You can never say that, because there's situations that I've never looked at that could react differently. But in our cases, 17 site years, all those scenarios, we didn't see any reductions, even in really restrictive environments or fairly productive environments. Tillers are not yield suckers, okay? So we can't assume, because we see a tiller on a corn plant, that the yields are going to be lower. So if you have a farmer that calls you that says, I see tillers, my yields are going to go down, I'm really concerned about this, we can't make that assumption. Just because there's a tiller does not mean that you're going to have a yield reduction, okay? That does not mean that you're going to have lower yields just because tillers are there. And the last one, which I think is one of the more big picture ones, is that if you have tillers, you have a plant density deficit, okay? Not to say that that's true for the whole season, but let's say you go out at V5 and you see tillers coming on. In that moment, at V5, you have a plant density deficit. Those plants can tell, they're reacting, say, hey, we've got space, we've got resources, there should be more of us, so they're putting tillers on. But later in the season, if water dries up or something else happens, that plant density might end up being, optimum or about right. But just in that moment when you're seeing tillers, you do have a plant density deficit, okay? But hindsight is 20/20. The optimum plant density is a term we throw around, but it's impossible to know what that is until the season is done, okay? You don't know what the weather's going to do. You don't know what's going to happen. You can guess, we can predict, we can put models on it and say, yeah, this is ballpark, but we don't really know for sure until the season's over. And so tillers, if we are managing defensively, trying to get to third base, right? Trying to at least get that far, they can help us salvage a surplus of resources if the year is better than we expected, right? They can kind of help us. They're not as good as more plants, but you can't really go out and put more plants in mid-season, right? That doesn't really work. So tillers are kind of a insurance policy, so to speak, of at least salvaging what we can, even if it's not as good as if you would have had more plants out. So that was what I had for you. My voice held out. I do have a website where we keep a lot of stuff related to this project. My email is there. I'm extremely active on Twitter, so all of my research stuff gets put on there. I'm scheduled to graduate this December, which means I have 3 more chapters of my PhD to get published, which means that there's going to be a lot for me in the next year, and that's all going to be on Twitter, I'm sure. So, but yeah, would love to hear from you. If you need access to those resources or have questions, if you have tiller pictures, tag me on Twitter. But if you have any questions or comments or anything, there's been really good discussions in the last couple sessions, really good questions. But I would love to talk about anything you'd like. Thank you.